Okay, before we get into coding and actually looking at examples of it running live, it's worth having a few minutes just to introduce the concepts of OpenMP and some of the sort of things behind it in terms of threading and the models that it uses in order to accomplish what it does. So a couple of definitions, a couple of things from online, openmp.org. The OpenMP API supports multi-platform, shared memory, parallel programming in C++ and Fortran. The API defines a portable, scalable model with a simple and flexible interface for developing parallel applications. Wikipedia, OMP is an application programming interface that supports multi-platform, shared memory, multiprocessing, and goes on to list a bunch of behaviours. It consists of a set of compiler directives, library routines, and environment variables that influence runtime behaviour. So, a couple of important things to highlight. So OpenMP is all about shared memory parallel programming. If you look at the wider introductions into different models of parallel programming, this is SMP, so we are operating with threads. So these are things where the memory and the context is the same, so we can share variables, we can share resources between it, but we're executing across multiple cores on the same highly linked backplane. The second thing, which is one of the reasons why OpenMP remains incredibly popular, because most languages, or probably all modern languages anyway, have very decent implementations of threading and ways of accomplishing, shared memory parallelism. But OpenMP provides an abstracted API that works out of the box on different platforms, and that's not as easy a given as you'd think. If you're dealing with low-level languages, so C and C++ we're talking about here, the threading varies widely between operating systems. So if you're trying to write code that does high throughput computing using threads, you can require an awful lot of boilerplate and platform-specific code to go into it. Whereas if you're using OpenMP, it's the same library and the same directives that then compile time handles the transfer into whichever particular underlying threading implementation is used by the operating system. OMP uses a model called fork join. So this is probably the most common model of threading. And with fork join, what happens is, if you imagine a single thread of execution, program, sort of traditional single-threaded program, is a single thread going through. At the point where threads are spun up, they are forked. So forks are where new threads are formed, which have the same memory context as the existing thread. They do the work, and then at a certain point, and that might be the end of the program, it might be a given point when the parallel region ends, there's a join where the threads come back together. And it's a pretty standard design pattern in parallel programming. This is what it looks like in terms of fork join. So and the terminology used here is master thread. We might also use main thread or whatever. But the primary thread, thread 0, goes through performing its operations. When it reaches this parallel region in question, threads are formed and we break into parallel. So we fork apart to do the work, and then at some point we join back together. And in this example here, you can see we actually have 3 sets of parallelism, and at each point we fork apart to the necessary number of threads to do the work, and then we come back together at the end once that parallel region is finished, or we have finished the question. Here is what it would look like if we were executing in sequence. We would just go through, and obviously we can only do one thing at a once. So we're doing A, then B, then C. Whereas with parallelism, we are concurrently executing A, B, and C at the same time. OpenMP works by marking up sections of code. So we put compiler directives, pragma directives in, which allow us to influence how the underlying compiler then makes the threading happen in terms of the platform-specific implementation. And then the sections are executed by the terminology teams of threads. So a team is formed of threads, and these then execute the world. How exactly they work, and how they work in terms of the numbers, how memory is shared between them, how things are protected, there are myriad and many options. But the important thing is that they are abstracted away from the underlying implementation, whatever that might be, whether we're compiling on Windows and we're using or compiling on Unix and we're using POSIX threads, it's abstracted away. So we just determine what we want to happen, how we want memory to be shared, what items we want to be in scope, etc. And then that's handled for us. So in C, all we need to do in order to do this is include the library, omp.h, tell the compiler and linker to use the library, so that requires the OpenMP library to be installed. Certainly with GCC, it's installed by default on most installations of GCC, not always on the standard one that comes with the Mac, but on the actual official GCC version. And then we use these compiler directives, pragma directives, to determine things like where to begin parallel regions and also the settings that we want OpenMP to operate with. And then once we're up and running, we can also use OMP methods specifically to interact with the OpenMP system underneath.